This is a weekly summary of interesting news that is relevant for my distributed systems lecture at the Eastern University of Applied Sciences in Switzerland. My name is Thomas Borczek, and today we will discuss 5 topics. The first topic, it's the following topic here. This describes how to run Ubuntu on RISC-V using QEMU virtual machine without actually owning a RISC-V hardware. And RISC-V, this is an open instruction set architecture. And for software portability, there are standardized baselines called RVA profiles, and Ubuntu 24.04 targets RVA20, and with the latest Ubuntu 25.10 and 26.4, the requirement moves to RVA23, which adds features like vector and hypervisor extensions. And RVA23 was ratified in October 24, but no RVA23 compliant boards are available yet. Several are expected around April-May 2026. So instead of buying non-existing hardware, here the author emulated RISC-V using QEMU on his Intel ThinkPad, and he installed Ubuntu Server, then the desktop environment. And he mentioned the emulation was very slow since every instruction is translated into software, but it was enough to confirm their application launches and runs on RVA23. And in lecture 3, I also showed Ubuntu running on RISC-V. So this is a practical example of the same idea, testing software on different instruction set architectures through emulation. The next article is about Docker and Podman. Red Hat released an enterprise build of Podman Desktop, a graphical tool to manage containers, images, pods, and local Kubernetes. It works on Linux, macOS, Windows, and it's a direct competitor to Docker Desktop. The enterprise build adds Red Hat support, security fixes, and tighter integration with OpenShift. And the tool supports Docker files and Docker Compose, making migration from Docker easier. And the container desktop market is getting crowded. We have Docker Desktop, Rancher Desktop, and Portainer. And I think Red Hat is betting that OpenShift integration and policy enforcement will give organizations already on the Red Hat stack a reason to choose Podman Desktop over the alternatives. And the Docker compatibility should also make migration from Docker to Podman easier. And in lecture 3, I showed Docker from the command line, not through a desktop application, but you can use either. The next article is about vendor lock-in, and it's the following article here. 2 years after Broadcom acquired VMware, the predicted mass exodus of VMware customers has not happened. According to a survey by CloudBolt, the following site here, only 4% have fully replaced their VMware infrastructure. However, 86% are actively reducing their VMware usage. The price increases were real but less extreme than feared. In 2024, 73% expected their cost to more than double, and in reality only 14% saw increase above 100%. The majority experienced increases in the 25 to 50% range. That said, some organizations reported extreme cases of 350 to 700%, and EU cloud providers documented increases of 800 to 1,500%. Migrations are slow and it is hard. And this is an example of how effective vendor lock-in can be. And this is why staying with generic non-proprietary solution is often a better approach than committing to a specific platform. The study suggests Broadcom is deliberately accepting customer churn while maximizing margins for remaining customers. However, it's worth noting that this site at CloudBolt sells VMware migration tools, so their report may not be entirely balanced. The next article discusses sandbox isolation. It's the following article here. This is for running untrusted code. The article presents a spectrum of isolation approaches. The Linux kernel exposes 370 or around 370 syscalls across tens of millions of lines of code, any of which could contain a bug. Linux namespaces, as used by Docker, restrict what a processor can see but still shares the host kernel. Seccomp filters, which syscalls are allowed but still uses the same kernel. gvisor intercepts syscalls and handles them in separate user space kernel, reducing the number of host syscalls. And microVMs like Firecracker give each workload its own kernel with hardware-enforced isolation. WebAssembly provides no kernel access at all. Code can only call functions the host explicitly provides, though language support the author mentions is still limited, but major languages can compile to WebAssembly. So here I don't fully agree with the author. And I showed namespaces and microVMs in my lectures, but I did not cover WebAssembly here. For me, WebAssembly, it's more a portable compilation target than an isolation mechanism, but it's interesting that it is mentioned here as a sandboxing approach, since unlike the JVM that also had a security sandbox but was eventually deprecated, WebAssembly was designed with isolation as a core feature. And then there are many articles about GenAI and the impact on software development. Each of them have interesting viewpoints. So the first article about AI here, this article compares vibe coding to the maker movement, which faded when value flowed to manufacturers rather than individual makers. And the author argues vibe coding skipped the playful learning phase and went straight to production. So people produce real output but lack the judgment to evaluate it. This article reflects on how software engineering is shifting from craftsmanship to mass production as AI writes most of the code. The author argues that fundamentals like architectural taste, good engineering practices, and understanding constraints still matter, and that tools already used by good teams, for example, small diffs, CI/CD, automated testing, also happens to work well with AI agents. However, beyond a 5-year horizon, the author is less confident that these human advantages will hold. This article introduces the concept of cognitive debt, the gap between how fast AI lets engineers produce code and how fast they can actually understand it. Unlike technical debt, cognitive debt is invisible to velocity metrics. Code works, test passes, features shipped, but no one truly understands the system. The debt compounds over time through shallow code reviews, loss of institutional knowledge, and junior engineers who never develop architectural judgment. The last article here argues that AI coding creates a hidden cost. Skills you stop practicing decline, and the more AI writes, the less qualified engineers become to review its output. A study found that developers who fully delegate to AI scored 70% lower on understanding and debugging the exact skills needed to supervise AI. And the right amount of AI is neither zero nor maximum, and the author warns that metrics show improvements while engineers quietly lose the ability to reason about their own systems. Well, I believe that GenAI will fundamentally change how we develop software. It will become more goal-oriented, and the coding craft itself will become less relevant. One article says or mentions that engineers understand the produced code less. On the other hand, I do not fully understand what assembly opcodes are generated when I compile, for example, my Go code. I know the basics, but I lack the details, and I think this will be similar with GenAI. However, there is an important difference. A compiler is deterministic and well tested, while AI-generated code is not deterministic and can be subtly wrong. I think we will write less code ourselves and supervise more, and the total amount of code will grow significantly, including AI slop. That means we will spend more time navigating and reasoning about large code bases we did not write and do not fully understand. Instead of understanding every line, we need to understand the patterns and ideas behind the code and learn to ask the right questions to figure out what was produced and how it works.